And let's start now. Thanks.
Okay. It's a great pleasure to have Han Yu from University of Cambridge as our speaker today. And he's going to tell us a little bit about rational points near self-similar sets. Now, Han, the floor is yours.
Okay, can everyone hear me?
Yes, I think so.
Okay. Let me get the full screen image. Okay, so thanks the organizer for the invitation. So I will talk about some problems and some results on rational points near self-similar sets. And actually, a major part of this talk, is joint work with Demi, Sam, and Peter. Okay, so let me start. Can everyone see that I'm already moving to the next page? Okay, I think so. Okay, so first I want to remind you what missing digits measures means, because there will be the central thing in this talk. So basically, it is like the middle third counter set or the middle third counter measure. You just start with an integer p as a base, and then you choose a subset of digits, and you consider all the number that whose base p expansion do not contain only contain digits in D, and you put a very natural measure on top, and this is just the most natural measure you can think. You put on the set, the missing digit set. Okay. So after we agree on the definition here, let me go on. So the key problem or the idea is as follows. So how rational numbers are distributed near missing digit sets. You can have in mind the middle third counter set as.
Can you let knock out on the leash?
Sorry. I think I hear your question or something, or not. Okay, so maybe I continue.
Yes.
So the problem is as follows. So for example, you have the middle third counter set, which I can draw a little bit, not too much. Why there is an arrow? I don't know. So you have this sort of counter set, which is a fractal, and you are interested in like whether how the rational numbers are distributed around this special subset, and as long as you want to get some concrete example, for example, the simplest thing for the middle third counter set is you consider the rational numbers with denominator 3 to the powers, and you can see that in this case, the rational numbers are not equally distributed around the middle third counter set, because of course they prefer rational numbers with denominators to some power. But this is not the end of the world, because we can still think about how rational numbers, in general, like all rational numbers, distributed around the missing digit set. So this is the key problem. And so we have some intuitions or ideas in mind. Wait. Okay. So first, this intuition comes from the work of Kleinbach and Margulis. So if you have a curved enough manifolds, means that the manifold is not degenerate of some sort. So if the manifold is curved enough, you consider the Lebesgue measure on the manifold, and then the rational points are very well distributed around this manifolds according to this Lebesgue measure on the manifold. So I would explain a little bit more about what I mean by no more, no less, but you just have in mind that there should be just the right amount of rational numbers around such manifolds. This is the first intuition. And the second one is those fractal measures. You can think of them as being curved in some way. Of course, if you consider fractal measures on the line, I mean, there's no real curvature. And but in some sense, they behave like they are curved. And the precise meaning will be carried by a Fourier analysis, which I will definitely illustrate. So this the study of Fourier transform of fractal measure is I'm not sure it's have been explicitly set up somewhere, but it is like a very old topic. People from maybe 100 years ago start interested in this sort of thing. Even before the notion of fractal set was there. Okay, so I will illustrate this second idea a little bit in more detail later. But let's think about the third one. So the third one is just okay. You should believe that if a fractal measure is somehow very curved, it should behave just like curved manifolds. And in this way, you should also believe that the rational numbers are very well distributed around those super curved fractal measures. And the last idea is that the curvature is carried by the decay property of Fourier transform. So if you just think about these four ideas, you link them together, and then you should already have a rough program in mind. How to study this counting rational numbers around fractal set. And in fact, in this talk, I will just sort of making every idea in concrete, more concrete. Okay, so what I say by why this Fourier decay or some sort of curvature is very related to rational counting is as follows. So if you have if you start with a measure, okay, I'm not really say anything, right? So mu is a measure. What happened? Why I cannot? Okay, I don't know what happened. Why is always regular? Okay, I'm sorry. The program sort of want to correct what I'm writing, but it's not helpful. Okay, you think about mu as a Fourier probability measure supported on R or Rn, does not really matter. So let's say if it's supported on R, and then if the Fourier transform of mu decay to 0, then it corresponds to the fact that if you times q is an integer, q times mu means that is the action times q modulo integer. And this measure should converge to the Lebesgue measure as q is large enough, but maybe at a very slow rate. That depends on how fast your Fourier series decay to 0. So this is this first correspondence. And
excuse me, can you clarify? So mu is the measure on the real line?
Yeah, mu is a Fourier probability measure on the real line.
And then how do you make it mod 1? You make a measure on the circle then?
Yes, you make it a measure on circle by consider the modulo 1 action.
So it's a push forward, just a push forward.
Yes. Yeah. Or maybe you just start with the measure supported on the unit interval. Maybe that's also okay. Okay. So this somehow I cannot write what I want to write. Okay. Never mind. So this correspondence tell you that if the Fourier transform, the first coefficients of your measure decays to 0 very fast, then the Q rational numbers are somehow very well distributed according to mu. So Q rational numbers are those rational numbers with denominator exactly Q. So that's the first idea. Okay, you can think about it. So the Fourier transform of mu basically tell you that the local fine structure of mu up to some scale. And if the Fourier coefficient is small, equal to 0, that means that in some sense your mu is close to the Lebesgue measure if you just times Q in this way. You can make the argument process, but this is not the main point of this talk. So, but we have the second idea. You know that, for example, the missing digits measure we just introduced in the beginning of this talk, they don't have any Fourier decay property. So the Fourier transform do not decay to 0. In this case, we should think about something else. So we cannot study the distribution of rational numbers with fixed denominator, but there's a hope to study distribution of rational numbers with bounded denominator, for example, bounded by Q. Actually, if you think about the idea 1, the converse of the idea 1 is also holds true. So if your Fourier coefficient do not decay to 0, then it means that at some level, if Q is equal to some special chosen integer, then the distribution of those rational numbers are very bad, not well distributed according to mu. That happens for the middle third Cantor set, for example, if you think about the Q as being power of 3. So the idea 2 have a chance to be studied for missing digits measure, and this is actually our topic for today. You can see that the idea 2 is just a weaker version because it's just the average version of idea 1. Of course, if you can get already idea 1, then idea 2 holds trivially. Idea 1 tell you that the distribution holds individually for each Q rational number for each Q.
Excuse me, it's a question. In the equivalence by idea 2, you mean again on the right hand side to the Lebesgue measure, right?
Yes.
It's not written. Just
yeah, it's not written. It's the converge to the Lebesgue measure. That's the same as the idea 1.
Okay.
So
thank you.
Yeah. Yes. Q mu mode 1 on average are close to the Lebesgue measure. Yeah, this is what I want to say. Okay, so this should be Lebesgue measure. Okay, so let's move on. So I want to mention a little bit about the Fourier decay property of self-similar measures, which is like a topic which is interesting on its own. So first, we have this result that like most of self-similar measures have polynomial Fourier decay in a very descriptive sense that you can actually construct the set of exceptions and study how large the set of exceptions. So the set of exceptions is not very large. But the problem is that the set of expressions, of course, is not very large, but it's not like really descriptive in the sense that we can check whether or not self-similar measure belong to or not belong to that class. So this is a generic statement. Polynomial Fourier decay here means that if you make the Fourier transform of mu, and then you study I don't know what happened. So I hope everything is fine. This decays in a polynomial rate. So it's t to the power of minus sigma with sigma positive number. So this is what I mean by polynomial decay. So this is the first result. And the second one is that what if we do not care about polynomial Fourier decay? What if we just say that, oh, we want to study the self-similar measures which do not have Fourier decay at all? Then we have a roughly concrete and very complete result by Lee and Susten, Brimont, Varju, and myself. And very, very recently, Rappaport studied this result in any self-similar set in Rn. All the results before in those papers only concerns self-similar measures on the real line R. But very recently, our report studied the self-similar measures on Rn for any n. And this is actually a very strong result. So actually, essentially, those self-similar measures without Fourier decay are very special in the sense that their contraction ratios need to be powers of the same Piso number. So it is something, Piso number is a certain class of algebraic number. And all the translations also lie in the field generated by this Piso number. That's actually, this is the result on the real line R, and the real line on the in Rn, Rappaport's results is similar, but in Rn you have something more complicated, some regarding the rotations and stuff. And
could I ask a quick question?
Yes.
Sorry. When you say they have polynomial Fourier decay, are we talking about the average Fourier decay from idea 2 or the
idea 1, the pointwise Fourier decay?
Pointwise, okay, thank you.
Yeah. So everything I'll talk on this page about pointwise decay. Yes. So okay. So the point is that now we have a very good understanding about the Fourier decay property of self-similar measure, all self-similar measure. I mean, roughly satisfactory. Not satisfactory because we do not have any idea about this polynomial region. This something is uncertain. Okay. So far about the self-similar measure with Fourier decay, and now I want to go on about this lattice counting. So we know that in one of the previous pages, you know that the Fourier transform property is directly linked to this distribution of rational numbers, and I want to make it more clearly. So I want to say that how to count rational numbers near a missing digit set or according to a measure mu. It means that I want to create a little ball around the points on the lattice, for example, all the rational numbers with a fixed denominator. And this set A, delta Q is precisely the set. Although maybe let me try one more time that I can maybe draw whatever I want. Maybe this time it works. So the set A delta QQ is like this on R. It looks like this. So you are on 0 and 1 unit interval. Then you consider all the rational numbers with the denominator Q, and like this. And you create a little ball around each those points. And this is actually those little balls are intervals. And then the union of those intervals is the set A. And delta Q is the scale. It's basically the radius of the little ball. Actually, the radius of little ball in this way should be delta Q over Q. Okay, so and this is the thing. And this is actually, when I do the next page, then, oh, okay, this thing just disappear. Never mind. And of course, you can also consider the similar stuff on Rn. Is nothing is wrong if you study the problem on Rn, not on R. Okay, so the thing by lattice counting and problem for mu is that you just start with the Fourier probability measure mu, and you recall the set A delta QQ constructed in previous slide. Just to recall your definition. Okay, you want to know how large is the set A with respect to the measure mu, and this is the lattice counting problem for mu. And there are some intuitions that should have in mind. So mu has super counting property, means that the counting property is just very nice. This is what I mean by no more, no less. More or less, right? So no more, no less means that the mu measure of the set is more or less equal to the big measure of the set A delta QQ. So this I would say no more, no less. Of course, this thing depends on what happened. Depends on the size of data queue, and if data queue is very large, this thing should hold trivially. So really the question to ask is how small you can let this data queue be to have this property. So I need to actually have this. So this condition for alpha is bigger than 1 is actually something that's actually very strong. So you can choose data Q to be, for example, if you this host, for example, then you can choose data Q to be 1 over Q to the power of alpha minus any epsilon, which epsilon is something bigger than 0, which definitely means that you can make this exponent to be bigger than 1. That's the point of this. Okay. But sometimes you do not have really this property. Somehow the supercounting property, maybe it is too strong. And this actually correlated to the idea 1, that you have the pointwise Fourier decay. So if you have a Fourier decay that is fast enough, you definitely can prove result like this. But in some cases, the most interesting case, we do not have Fourier decay at all, then we need to study the other averaged version. That is correlated to the idea 2. So on average, you have this counting property. So this means that on each level, you should roughly have this data, and then you have capital Q many levels. So this Q times data. That's the averaged version of super counting property. Okay, so these are the 2 counting properties that you are looking for self-similar measure. And in this talk, we concentrate on the second one because it can be proved for the missing digits measures, which are somehow of interest in this talk.
Han, could I ask a quick question?
Yes, sure.
So about idea 1.
Yes.
Can you hear me?
Yes, I can hear you.
Yeah. So about idea 1, can you make a quick connection between the notion of extremality and supercounting? Is there a statement that relates these 2 properties?
Yes, I think so. On R, of course, at least, supercounting property actually, I think, implies extremality.
So for example, let's take the middle third Cantor set and the Hausdorff delta dimensional measure on there. Well, then
yes.
That was one of the first fractal measures to be shown extremal by Barak Weiss.
Yes.
And so is there a supercounting for that measure?
No, there's no supercounting for middle third countermeasure.
I see.
Actually, it's a good. Actually, I'm not sure whether there's a good counting property for middle third. I will mention this. But thanks for pointing this out. So it gives the audience something to think about. So you can all think about this problem, whether the middle third counter set have supercounting property or not. Of course, I will say that have supercounting property will imply extremality, but the other direction does not work. So this is one way thing.
Hey, Han?
Yes?
What do you mean by extremality?
Oh, extremality means that you can, the mu measure of, I believe, well-approximable points equal to 0.
Very well approximable.
For all the mu bigger than 1. I will tell you what this set is very soon, so you will not miss this. So this is the notion of extremality. Of course, extremality also extends to a higher dimension as well. Then you always correlated to this property.
Thank you.
Yeah, and you will know what is this W mu very soon. Okay, so let me go on. So the mean result we have in this talk is this. So the middle fifth countermeasure has GCB, the good counting property. Let me remind you what is the good counting property. So it's on average, it's really nice. The behavior is really nice, and then we can actually show this for the middle fifth countermeasure. This thing holds. Okay, so the question is, leave the remark. We do not know whether or not the middle third countermeasure has this GCP or not. In fact, I think so. We did some numerical computations, like super explicit and rigorous numerical computation, which can be counted as proof. So we showed that as long as P is bigger than 5, all writing this down is probably all missing digits measure. I cannot write it. Okay, so as long as the base is bigger or equal to 5, if you have a missing digits measure with only one missing digit, they all satisfy GCP. And actually, okay, I will return to this topic very soon later. There are some delicate issues, and which is I think is interesting, and I will illustrate it later. So for now, we just do not know whether or not the middle third countermeasure has GCP or not, and it's just that our method does not cover this specific countermeasure. And
can I ask? Yeah. But is middle fifth Cantor measure a missing digit measure?
Yes. Oh, okay. I always. Oh, okay. I think it is a missing digits countermeasure. It is a base 5 without digit 2. So base 5 expansion without the digit 2. This the middle fifth countermeasure. Of course, I think this.
But
I know.
That's not the same as erasing the middle fifth, and then the remaining middle fifth, and so on, is it?
No, it's not the remaining the cutting procedure. Maybe I should not say the middle fifth. I can see that you think that the middle fifth means that I cut the middle fifth and then I cut the middle fifth like this.
But
no.
So you remove the middle fifth from each of the 4 remaining fifths.
Yes, but what I mean is that you cut the unit interval with 5 pieces, remove the middle one, and then for the remaining 4 you do the same. That's yeah, I see this so in this way it is a middle fifth countermeasure. It is a missing digit measure. Okay, so we can test. So we can do all missing digit measure with one missing digit with base that is at least 5. So that's everything we can do. But smaller than 5, there's some delicate issues. I will mention. But before I mention those delicate issues, maybe let us see some consequence that we can draw. One of the motivation to study the distribution of rational numbers around some set or measure is about Diophantine approximation. So the metric Diophantine approximation. So if your measure has GCP and your measure is AD regular, which is like, okay, all the missing digits measures are already AD regular, it covers our example. You should have these 3 convergence results. By say convergence results, I mean that you can always sort of get an upper bound of the counting. And then as a result, you get the convergence theorem, Kitchen theorem. Okay, so maybe now I tell you what is the well approximate number. So nu is a number that is in our case it should be any real number, but in our case what would be interesting is mu is a real number bigger than 1. So this is a new very well approximate number, new well approximate number. So you have this 3 sort of upper bound of some counting, and you can prove correspondingly those results. And the Diophantine approximation is not the main topic of the talk today, so I will just be very brief about them. The first 2 were some problems of asking or speculating around for a while, and the third one, I just came across the third problem actually very recently. So I want to mention a little bit further on the third problem. So it's counting the rational numbers in the missing digit set. So this thing. So because we have a very good estimate of the number of rational numbers around nearby a missing digit set. So this is actually an upper bound for the rational numbers inside, right? Okay, so the one word about the third point. So the third point was around I think quite recently, and there are some questions. So the strongest conjecture is in this form, that you have this counting. The number of rational numbers with denominator at most q inside a missing digits measure should satisfy this upper bound counting constraint. Yes, this for me looks very, very strong, because this something very delicate must be involved, because for the Lebesgue measure, does not hold for Lebesgue measure. Lebesgue measure you need to replace by 2, which is 2 times the Hausdorff dimension. But with our method, we can reveal some of the delicacy. We call this result we have. So the result we have is with this exponent. So if your measure has GCP, means that you can choose alpha to be bigger than 1, then this exponent is strictly smaller than 2 times the Hausdorff dimension. So it's strictly smaller than there's this bound that we had before, or not in this talk. So we can reveal some of the delicacy, but not all of them, because I mean I could imagine that maybe it is very hard to get to this point. Okay, that's my words on the third point. And to remind you what is the third point, should I flash it back? I cannot flash back for some reason. Okay.
Excuse me. So the AD regular means exactly what you wrote, that the measure
Yes.
of ball is proportional to the power.
Yes, with the S is actually in this case S is then the Hausdorff dimension of mu, or
Yes.
Hausdorff dimension of the support of mu.
So AD means absolutely decaying, or it's related to alphas? What is the connection?
Alphas David regular.
Alphas David.
Okay.
Okay.
It's some name.
Okay.
Yeah.
One question is it true really for almost? Is it true for all BR, or are there some exceptional points? Do I remember this wrong? Is it all?
No. For AD regular, it should hold for all, not almost all.
Oh, okay. Thank you.
Yeah, the AD regularity is a very strong property for measure, and it holds for missing digits measure. Actually, it holds for all self-similar set with open set condition in this case. It holds more general. And very fortunately, it covers our example. Yeah, so that's so far the I want to mention about the upper bound, this convergence part of dual fountain approximation, and about the rational counting inside self-similar set, or no, the rational counting inside the missing digit set. But if we exploit the similarity, self-similarity of a missing digit set, then we can actually prove some lower estimate, because if you say that some so the counting property we had with respect to mu, if mu is self-similar, we can then transform the global counting property to local counting property. So we know that how those rational points are distributed in a small area, which is the subset of this missing digit set. So we can actually understand this very well. And if we can understand those things very well, then we can actually get this lower bound result, which somehow in most of the cases are more interesting than the upper bound result. I want to mention two things. So first, as you can already see for the third point, I will say that the Hausdorff dimension of mu is very close to 1. I need to specify what I mean by very close to 1. So the condition we need is that the Hausdorff dimension multiplied the L1 dimension is bigger than 0.5. I will tell you what is this little L1 dimension very soon, but this is just the condition for 3. And you know that if there's this is actually something very strong, because both of the dimensions are smaller than 1, and to make the multiplication bigger than 0.5 is not easy. It's not an easy thing. I did some not non-rigorous numerical computation, and I think with base 10, 1 missing digit to satisfy this already. So in particular, the third point can be proved for the missing digit measure with base 10 and with 1 missing digit. Maybe even with 2, but for this I'm not sure. I need to check. But for sure it holds for the middle, the 10 to the power 7 plus 1. That's I did some rigorous computation last year, I think. So it's not 10 to the power 7 plus 1 is not very large. It's a finite. This is a finite number. This is the first remark I have, and the second one about the first point. For the first point, so for first point, the Cartier and the Lucci's result, actually they get a sharp kinshing theorem. The divergence, they get a divergence kinshing result for all large enough self-similar set with open set condition and rational parameter. For what I mean by a sharp kinshing theorem, for example, their result applies to approximation function like this, while we need to get a iterated logarithm, but in the 1 log should be already enough. And the other thing is that their result holds for their result have the condition that as long as the Hausdorff dimension of the self-similar set is large enough, then everything, then at least the first point holds. So Hausdorff dimension in most cases easier to compute than the L1 dimension. So the result holds more general.
Okay,
I think the result holds.
But can I ask briefly? So when you say that mu is a missing digits measure with GCP, it means that it's not enough to just have GCP. You need to know a lot more, right? So there's no statement that good counting property implies all these wonderful things. Is that right?
Wait, let me recall.
Well, maybe.
Yes. Okay, yes. Not GCP from GCP. You from GCP you can derive the first one.
The conversions. Oh,
but
the first one is okay.
Also the divergence. Yes.
Okay. That's interesting.
GCP is enough.
So let me rephrase the question slightly. So take this instead of digits, take the Gauss map and continued fractions.
Yeah.
And just build a fractal, for example, such that continued fraction coefficients are bounded by 1,000.
Mm-hmm.
So it's kind of a missing digit, but for the other expansion.
Yes.
So will it have good counting property? Will this? I think these are called.
Depends.
You're
I know
sure?
that this you can this set is you can find a measure that have polynomial Fourier decay. I think. But the polynomial Fourier decay, the power is so small that it will not trigger the GCP criteria.
Mm-hmm.
So I do not know whether whether those badly approximable number would have GCP.
But those are but probably you do because there is no divergence case. Then they're all badly approximable.
Yeah,
so for the function for the function 1 over q, there is no even for this function there is no divergence case. So I guess
probably they do not have GCP.
I see. Okay. Thank you.
They should not have GCP in that case. Yeah.
So could I follow up?
Yes, sure.
With one quick question. So you said GCP implies at least the first one, but you don't even need self-similarity to get like local estimates.
I need GCP plus self-similarity. So missing digits measure with GCP. So that implies self-similarity, but with the
and that's for all 3 points.
I thought that for, but now I think about for the second or third, I rather need the condition that trigger GCP than GCP itself. So okay, so maybe for the second and the third, some extra conditions are needed. So extra condition need. I cannot write it down. But okay, so this point is a good question. So for the second and third, missing digits with GCP alone might not be enough, but you need a stronger criterion to trigger GCP, which anyway holds for missing digit measure with GCP, all those measures that we found.
And for one, you still also need missing digit or some kind of self-similarity.
Yeah.
As well.
For one, I need self-similarity.
Okay, thanks.
Yeah. Okay, so let me. I think I'm in the middle of the second remark somewhere. Maybe I finished the second remark already, right? So their result depends only on the house of dimension, and in most cases it's very simple to compute the house of dimension of self-similar set with open set condition. I think the result actually holds, if I remember it correctly, for base 7 or something with 1 missing digit, something like this. Okay, so this is a nice result. I recommend you to read. So let me go on for the next page. So I promise you that I will give you the definition of this little L1 stuff, right? So this is the definition. The definition says that it's actually the LP norm, so some sort of LP norm of the Fourier series. If you have some sort of upper bound, then I will define this the thing here as the dimension you have. And I think I mentioned somewhere, but I need to why what problems? Okay, so this not confused with the capital LP dimension. So that's something that I think I need to mention all the time. Okay, so we will only care about this little L1 and little L2 dimensions. And for our case, the little L2 dimension is equal to the house of dimension. So there's nothing new. And the little L1 dimension, if we apply
could you show us the definition again?
The definition, this definition.
Yeah.
So I will only.
No, I got it.
Yeah. So the little p is either 1 or 2 in our case. And the L2 dimension is equal to the house of dimension, and a little L1 dimension, by applying some Cauchy-Schwarz inequality, you have a general bound. Maybe I need to write the not in this way. It's somehow very confusing. So this in this way maybe it's better. Right. So the little L1 dimension is bounded in between the half of the L2 and the L2 dimension. Okay, let me just recall you this a little bit longer. Okay, let me go on. So we have this L1 and L2 dimension and their relation with GCP. The first one is that if the L1 dimension is bigger than 1/2, then we have GCP. This alpha can be even computed precisely. So if this little L1 dimension is bigger than 1/2, then this alpha is bigger than 1 in this way. And on the other hand, we have a converse result. That is, if the L2 dimension, if the house of dimension is smaller than 1/2, then we know that this mu does not have GCP. But the problem is that this here is this L2 dimension, not L1 dimension. For example, the middle third contour measure, the L2 dimension or the house of dimension is bigger than 1/2. So in this case, the second point do not apply to the middle third contour measure. And this is a gap between L1 and L2 dimension. And my optimistic conjecture is that in both 1 and 2, we can just, I hope, just replace L2 by L1. But I'm not sure whether this is true or not. Do not be too optimistic. For me, as I could, I don't know how to disprove it either. So this might be true, right? So we get a very sharp. We should get a very sharp criterion of GCP. And so far we only have like a sufficient condition. Okay, so this is the relation between L1 and 2 dimension with GCP, and now I think I can go back to the Diophantine approximation part and give you the exact condition of some point that I missed. So for the second and the third thing to hold, you need not only to have GCP, but the L1 dimension, little L1 dimension is bigger than 1/2. But I think for the third is already implied here because the Hausdorff dimension is anyway smaller or equal to 1, so this is already implied. So this is a stronger condition than the L1 dimension bigger than 1/2. But for the second, you need the L1 dimension bigger than 1/2 for this thing to hold. So this is what I mean by stronger, some extra stronger thing. Okay, so I think now everything is clarified. Okay, so I'll give you a very example of measures with L1 dimension bigger than 1/2, but they are not missing digit measure. They're just artificially constructed. You choose a missing digit measure with Hausdorff dimension bigger than 1/2, and then you make the convolution. And you choose the digit set to be, for example, form an arithmetic progression. Then the sum set is not increasing the analytic too much. Then your dimension is not doubled. You're not increased too much. In this way, you could have this at 1 dimension. Okay. Let me go on. So of course, this measure is not very interesting. The interesting measure should be this missing digits measure with base 5 or something, right? So I did we did some numerics. We waste a lot of computation power. And okay, so let me tell you what is mu5. So mu5 is the middle fifth countermeasure. So base 5 is missing digit 2, and this mu3 is the base 3 with missing digit 1. So this is the middle third countermeasure. So it is possible to show that. I think the interesting statement here is that for the middle third countermeasure, the L1 little L1 dimension is smaller than 1/2, so we cannot tell whether it has GCP or not. So in fact, it is possible to compute the L1 dimension for the missing digit measure with any precision if you use the computer to do it. But we still have to compute the dimension a little bit more for some more sets. So this is still a work in progress. But if you do not want to wait, you can check some other earlier numerical results that is worse than this. So I had some other earlier preprint that I work out the case for the middle 15th countermeasure and this middle, what I mentioned, the 10, 12, 7 plus 1, and this measure. And I carry out some computation, and I think they are fine. But the method I used before holds for general homogeneous self-similar measure, not only missing digits measure. And also my method also works for self-similar sets without this rational parameter, without rational parameter. But the price to pay is that the numerics is really terrible. So that's something, right? So let me tell you more about the numerical results that I actually, my own laptop, I use Mathematica 12. It has some numerical package, and I did some computation. Of course, we with Demi, Sam, and Peter, we did some concrete, like precise and rigorous numerical computation. But it's a little bit for me. I'm not. I haven't run it on my computer. So on my computer, which is not a good laptop. I'm not sure how I can trust the mathematical 12, but those results I have is as follows. So you see the interesting case for base 4 is that if you are missing 0, then the L1 dimension is bigger than 1/2. But if you're missing the digit 1, then the L1 dimension is smaller than 1/2. So that's something that means that something delicate happened there, right? So L1 dimension depends. L1 dimension depends on the structure of the digit set, while L2 dimension does not. So this is one of the things. And with base 5, everything is fine. And with base 10, I think everything is fine. But of course, I need to warn you that all the results comes from Mathematica 12, not explicit numerical package. So I'm not sure whether it can be used as a proof or not. So be careful if you want to use the result anywhere else. Okay, so these are the 2 numerical results I want to mention. And so, I mean, before I go to something else, I just say that combine the 2 results I just mentioned, you get the mean result. That is the L1 dimension bigger than 1/2 implies GCP, and then the some measure have L1 dimension bigger than 1/2. Therefore, some measure have GCP. That's the mean theorem we have. So before I proceed, any questions? Okay, if there's no question, I think I do not have time to show you the full detail of one of some proofs, but maybe I will illustrate the idea. At least I illustrate the idea, right? So why Fourier analysis is useful for lattice counting? It is precisely lies here, the Passivhaus formula, and this Passivhaus formula. I think this method is not new method. It's a very old method. I think it's known by Gauss, if I'm not mistaken. I think Gauss did not use the notion of Fourier transform, but I think he explicitly used the character sums and the orthogonality of and the complicity of character sum to prove some of his famous results. So it's sort of in the same idea. And the main idea here, I would say, is if you know that, like this is arrow. So if you know that this coefficient decays to 0 in some sense, maybe on average, very fast, then you can deduce that this sum, this integral, is basically captured out by the first term, which is the Lebesgue integral of f, and that lies in the whole idea. Of course, in order to do this, you need to have like basically a pointwise. Most cases, you need to have a pointwise Fourier decay for this procedure. But if you want to compute something average, you average here already, and then you carry out the average on the Fourier coefficient here. Then this actually lead to our L1 result. So which basically lead to this the first result result 1 I just mentioned. And then I wrote down the full details of how to derive the result 1, and I think I wrote down too many details, and I do not have time to illustrate them all. But maybe let me fast skip them. Most of the idea is very standard in nowadays harmonic analysis. So you just use a smooth approximation of the set A delta Q, and you just apply Passivhaus formula. And the difficulty, actually not difficulty, it's also very standard to compute the Fourier series of this approximation function you have. So let me quickly jump a little bit. not a little bit. Actually, I jumped all of them. So this is the key estimate formula we have. So this side is the integral we carry about, and we hope that it is equal to delta Q, or roughly equal to delta Q. And then our goal is to just bound the error term. And you see that from here, this sum of mu hat psi, you can actually factor out the mu hat psi out, because this divisor, you can bound the divisor. This d is the divisor. The number of divisor function is not very large. So you can do some manipulate this error term, and you see that the L1 wide L1 dimension is relevant, because if the L1 dimension is large, then the sum of these coefficients is small, and then it is possible to bound this error term. That's the whole logic or philosophy. Okay, so all the other steps I carry out is just to try to illustrate what I just said. And then after you do some computation, and you do a lot of computation, and then you do further computation, and then you get the result. That is, as long as you can choose some alpha. So this is the condition that you can draw from the above computations, and that's actually holds. This actually draws the result one I just mentioned. So one dimension bigger than 1/2 implies GCP, and like this. I mean, this is not a particular hard thing. It's just you do some computation. Okay, so I think I'm running out of time, but I'm running out of time. But let me just to show you one last thing. This is okay. So this is conclusion I want to show, but yet I want to show another conclusion. So you can apply the above arguments for Rn. So in Rn you have also Q lattice. So right, and you can do the same stuff. You put a little ball around each of the lattice point and use Fourier analysis on Rn or in Tn. The torus n-dimensional torus does not really matter. And you apply the above arguments, and sort of you can see that if you have a Fourier measure with pointwise Fourier decay, and the decay is too well, then mu almost all the number cannot be very well approximable up to some sort of parameter controlled here. If you have a nu bigger than 1/n and the decay is too well, then you have this. And from here you get another condition that is mu cannot be supported on well approximable vectors, right? Because if mu is supported on well approximable vectors, then mu almost all points must be well approximable. But on the other hand, the mu almost all number cannot be well approximable with the same parameter. So this is just, you get a contradiction. So from here, the conclusion is that I could not have time to show the Salam set, but this, you can use this argument to show that this set W nu is not Salam. Is you cannot find the measure supported on this set with sufficiently nice Fourier decay. That's actually something that can be done. Of course, this argument holds works in general. So you can actually. So I think there's many other constructions of well approximable vectors of this sort. You can, instead of this this norm, you can use some other norm, like use linear form norm or something. I think for all this, I think, I'm not sure. I do not take this word so seriously. I think the only Salam set that is coming from this this kind of simple construction would be those proved by Kaufman, namely the well approximable numbers on R. And in higher dimensions, you need some other construction. I think the other construction is carried out by Hamburg. I think he managed to construct Salam set with in any higher dimension space. I'm not taking anything wrong. Okay, so this is a bonus conclusion I can, as far as I can see, and that's really everything. That's really everything. This last slide.
Okay, thanks for the talk. Let's unmute ourselves and give our speaker a big round of applause.
Thanks, everyone.
Are there any questions for our speaker?
So can I ask a question about the previous slide, this bonus bonus
this
construction? So you have some general statement in Rn. So and then you in the beginning you started with this similarity between the curved manifold and diffract Fourier decay. So what does it mean? Suppose your measure is supported on a curved manifold, like an analytic manifold not contained in a hyperplane.
Yeah.
Then does this Fourier statement hold?
Yes, I think the Fourier statement holds.
So
but the problem is whether this measure have Fourier decay or not. That's something.
Yes, so that's my question. So do you have an alternative proof of our theorem with Margulis or not?
No. I at least not no. I think for hypersurface, that's definitely possible. For hypersurface with non-vanishing curvature, the Fourier decay. So it's a standard result in harmonic analysis. And I think there is also other results about Fourier decay of surface measures supported on manifolds, but it's been more complicated.
Yeah, I see. Oh,
more complicated.
For hypersurfaces, probably it was known before by Dodson and others. Although I'm not completely sure.
That's why I think it's at least not known. I think maybe to study the Fourier transform of the surface measure more precisely, you need more details for the Fourier coefficient. I think it might be possible, but I'm not sure.
Interesting. Okay, can I ask another question? Is it possible to show this L1 dimension definition again?
Oh, yeah, it is possible. It is possible. I need to scroll up.
Hard.
The definition to find it.
Must be somewhere
here.
Yeah. Okay. So so what is the quantification on this R, big R? I was confused.
The big R. The big R means R is just the positive number. So this is the asymptotic result. So
so it holds for every R or for some R?
Yeah, it means this asymptotic result means that for this holds for all large R.
So for all large R, this holds.
Yes, large enough.
I see. So how are you checking this with computers?
For me,
you just take large enough R and believe that
no.
all large enough will work.
No. We can only do it for missing digit set. That's
but I have a general question. How can a computer help to compute or estimate this dimension?
Okay, so this is something. I wish I can write it down. So for general, in the general setting, for general probability measure, there's no hope to do the computer check. But for self-similar measure, you can actually explicitly compute the Fourier coefficient. So the Fourier coefficient of this for self-similar measure is the product, sort of a product of some form, like this as maybe infinite. This should be infinite, and some function. Maybe P is the for example, P is the contracting ratio. Then you have this sort of. This may be cosine. This is not theta. This is not theta. This is cosine. So you have this structure. This thing. Of course, okay. This is already good. They tell you a lot of. This already tell you a lot of information. So one thing is that you write down the definition of this dimension, and you try to manipulate this sum, and for R large enough, and you can figure out that there is some sort of recursive bound. So you have if you have a bound for little r, you can upgrade this bound for larger r. And then you use this method to eventually bound everything for all large R enough.
Okay, but where does the computer enter the picture?
The computer enters by showing finite sum for a small value of R. And, the small you have a bound for small value of R. Then you can use this bound to generate a nicer bound for larger value of R.
Okay.
So this is a recursive procedure.
Okay.
And
very interesting.
The thing is that you hope that for some R you get a good enough result, in order that for large R you get a good enough result. That's something.
Okay. Yeah. Thank you.
Yeah. Yeah, that's basically the idea.
Okay.
Are there any other questions?
Can I ask a quick question?
Yes.
Is it possible to say something about, so in GCP you have the sum of the measures of these intervals over the denominators?
Wait, what with GCP? Let me recall the GCP property, right? Yes, this.
Yeah.
Yeah.
So is it possible? It's probably better to consider the measure of the union of these sets instead of the sums of the measures over little q, because somehow there may be some kind of overlaps.
Yes, that's definitely better to consider the union, but union is not easy to compute. So if you consider the sum, you use the Fourier transform. Then in the Fourier transform is also a sum, because Fourier transform is linear. But if you use the union, it's not easy to carry out the Fourier transform.
I see.
Yeah.
And for maybe to follow up on the previous question, so these missing digit measures are, I think, like times p invariant, where p is like the base.
Yes.
So does this say that like the Fourier coefficients that are far out are kind of related to the small Fourier coefficients, so one maybe doesn't have to use an infinite calculation?
Yes, that's actually exactly the idea. So the large Fourier coefficient far away related to Fourier coefficients nearby of some sort, and then you can use your finite information and push your finite information to infinite sequences. That's the key point. That's the key point to have the self-similarity, right? You have finite scale information, use self-similarity to gain detailed information about the finer scales. That's the idea.
Great, thanks.
Also, yeah. And then, okay, I want to mention one thing. The point that I cannot consider union here, they directly shows here where I cannot get the divergence result. So if it is possible to do, then then I can. Then that's why that's why your counting method is, in some sense, I think, more accurate in this way.
I see. Thanks.
You're welcome.
Okay, if there are no further questions, let's thank the speaker again.
Okay, let me also thank you again.
Okay, yeah, we'll be back next Monday.